Welcome to the micro engineering course. Today we see a micro tubes here. So micro tubes are nothing but a tubes that is used for the generation of a micro or a micro tubes that are used to amplify the microwave signal. So as we have seen that a conventional tube earlier, so that conventional tubes such as a tetrode, triodes, pentodes, these are the tubes that we have seen earlier, and that tubes could not be used at a microwave frequency. They have some limitations. So those conventional tubes can be used below 1 gigahertz of frequency or below that 500 megahertz of frequency. But if you go for the higher frequency, these conventional tubes not to be used. So that's why the micro tubes are generated or micro tubes are designed that will work at a microwave frequency. So apart from that, there will be a solid state devices. Again, those solid state devices to be used at a microwave frequencies as a generation as well as for the amplification. We'll see that a microwave solid state devices after this tube. So before start with the microwave tubes, we need to know about what are the various limitations of the that conventional tube. So what are those limitations? So limitations of a conventional tubes, as you know that tubes are nothing but a tetrode, then triode, then a pentode. Now these are about the tube. Now in general, what happen in the tube? So it has a cathode and anode. Okay. So simply we supposed to be consider that for a given particular tube. So if you see the diagram of a tube, so it has a cathode, we have a cathode and anode. So supposed to be your electron is to be propagating through the a cathode there. You can say that uh, that is about cathode here, and this one is about a plate. We supposed to be consider it is to be a anode now. So in between that there will be a grid electrode. Okay, that is about you can say this is nothing but a grid here. So now this one is a conventional symbol of a tube. So now cathode emits the electron, then it will reach to this particular plate. Okay, now this distance between that cathode and this particular plate, we say a anode here. So that will be minimum or a maximum. So then there are some limitations about the distance between that a cathode plate and this cathode. Okay, this plate anode and a cathode here. There is a limitation. And then grid is used here, and that grid supposed to be considered to provide the electron to be flow toward this particular plate here. Now this one is about the interaction region of a tubes here. But for a given particular tubes, these are the leads that is about we can say that leads of this tubes here. That is about a anode. This one is the cathode, and these are about the grid here. So now in this particular case, what happened here? So for a given particular tube, so their lead inductance and the inter-electrode capacitance will be varied. If we consider this tube to be operate at a high frequencies, then there will be limitations regarding that a impedance of a circuit at a high frequency. What will be the impedance at a high frequency? If you consider this particular circuit, this one is about a grid here, so that capacitance between this inter-electrode capacitance between this plate and a grid here, so that will be vary according to the what will be the frequency we are going to be considered. Suppose at a 1 megahertz here. For example, I supposed to be considered it to be work at a 1 megahertz. Then what happened? This capacitor, okay, this one is about inter electrode capacitance. We say that. So it will be around in terms of a uh, ohm, supposed to be, you consider that a input impedance of your tubes. In that case, it will be about approximately it will be about a 1 mega 1 mega ohm. Okay, but if you consider that a higher frequency, okay, if you use this tube at a high frequency, then the total impedance, if you calculate, so a that will be what, that will be degrade. Okay, so that will be reduced. So now because of that, what happened? So impedance generally it is depending upon the factor of what will be the uh, a capacitance, that will be interelectrode capacitance, or that will be generally depending upon that what will be the resistor in between this plate and a capacitor. Or you can say that for a given particular electrode, what will be the total reactance. So if that reactance is varying based on the frequencies, so what will happen? So in that case, this one is nothing but a triode. Okay, for this particular tube. If you consider that the frequency of this particular tube, operating frequency of this tube, if it is increases, then the effective grid to cathode capacitance. Okay, then we can say that this one is about this capacitance and this capacitance. Okay, so both the capacitance. That is about the interelectrode capacitance, this capacitance. Okay, so in that case, what happened? That grid to cathode impedances of the tube decreases because of that decrease in the reactance. Now, what happened here? So that here, if we increase the frequency, okay, if we increase the frequencies, then what happened? That reactance will be changes. Okay, so reactance will be decreases. Why that reactance decreases? Because of that interelectrode capacitance. If we increase the frequency, then reactance will be decreases. Okay, reactance will be decreases. Now, if supposed to be say that why this reactance decreases, because of that interelectrode capacitance will be decreases at a high frequency. So that's why we supposed to be consider that whatever the we have a grid to cathode capacitance, that is to be a small if supposed to be at a high frequency. But if you wanted to increase again further frequency there, then again it will be decreases, means reactance will be decreases. So that is the effect of what, a interelectrode, a capacitor. And in general, if you consider the equivalent circuit of this particular tube, so that interelectrode capacitance will be looks like a parallel with a tune circuit there. And then because of that, it will affect the frequency use of this particular tube there. Then again another one at a frequencies above the 1 gigahertz, because generally micro frequency is to be used at a 1 gigahertz there. So then if we can supposed to be consider the tubes above the 1 gigahertz, then what happened? The parasitic circuit inductance of this lead wire, again it will be increases there. Okay, so now what happened? That is about here. If we consider that 1 gigahertz there, and then what will happen? That inductance, whatever the parasitic circuit inductance of this, whatever the wires we have, so that will be again increases there at that micro frequency. So that's why the lead inductance of this particular tube, generally if you consider, so it will be in a parallel with the interelectrode capacitor. And then what happen, if you consider the net effect of that capacitance and this interelectrode inductance, so then net effect is to raise the limitations to the frequency, toward the frequency, which your frequency will be limit, or we can say that a tube could not be used at a higher frequency there because of that interelectrode capacitance, or we can say that a interlead, that we can say that LED inductance. And that's why we need to consider that a tube to be operate a below 1 gigahertz of frequency, or a below micro frequency there. So that is about one limitation. One limitation is about what? A interelectrode. We can say that interelectrode capacitance. Okay, interelectrode capacitance and a lead inductance effect. So here at a frequencies, so there will be a capacitance effect or there will be a inductance effect, and that will decrease the operating frequency of the a tube there. So there are the various ways to minimize that effect of this capacitance or this inductance there. So what are those various ways? We can reduce the electrode area or we can reduce that lead length. Okay, so this way we can reduce the interelectrode capacitance and a lead inductance effect, which area reduce. Okay, so in that case, suppose for this particular tube, so that area of the tube is going to be reduced there. This one is about a grid, anode, and a cathode here. So this will be reduced there. But if we reduce the area, this limits the power handling capacity of the tube. So means that tube cannot be used for the higher power there. Okay. So then now the limitations. If we consider that to minimize the effect of that interelectrode capacitance and a lead inductance, so then we need to reduce the area. Okay, we need to reduce the electrode area as well as we need to reduce the lead length. But if you reduce the area and the lead length, so then what happen? That power handling capacity of the tube is going to be reduced there. Then we can say that a interelectrode capacitance here we can say that that can be reduced. So when we reduce that interelectrode capacitance, then moving the electron from this cathode to tubes here. Okay, so this one is about a so this moving. So that will affect the whatever the transit time. So we'll see that a transit time is what time is taken for the electron to move from the cathode to the anode. That is about a transit time. So we'll see that what will happen to the transit time effect. So that is about a first is about we can say that a lead uh, we can consider that a lead inductance or a interelectrode a capacitance there. The next about a transit time effect. Now, if you consider that a transit time effect means this one is about another limitations of this tube while constructing because we are supposed to be reduce the area, then a transit time is going to be reduced. So transit time is nothing but what? It is the time required for the electrons to travel from the cathode to the plate. So here in the case of this one is about a cathode and this one is about a plate and this one is nothing but a grid. So this one is the time here. So electrons are generated and then electrons are focused through this grid and then it will reach to this particular plate. So that is nothing but a time required. Time required to travel the electron from this cathode to the plate here. Okay, so now this one is nothing but a plate here. So from the cathode. So that is nothing but a transit time. Now, if that spacing increases, then capacitance increases. If the spacing decreases, okay, the capacitance decreases, but transit time again reduces. Now, what happened if the transit time reduces? Now, we supposed to be use a this tube at a micro frequency, means at a high frequency. Now that now consider that at a high frequency, so what will be the time required for this cathode to move toward this particular plate? So now that particular period, okay, that transit time from the cathode to the plate, that is nothing but a period. Now that period, if you compare with respect to the micro frequencies, so then what will happen? Now consider that generally what we can say that a transit time is nothing but it is depending upon the spacing between the whatever the cathode and a plate here. Now then how much is the time required to travel from the cathode to the plate? That is nothing but a time period. So in that case, if it is a low frequency signal, So then that effect, transit time effect or transit time effect will be appreciable at a low frequency. But at high frequency, in the case of high frequency, what will happen? That transit time period will be a low there. Okay. So at a high frequency, which in general we say that here. So what happened if we supposed to be consider that your tube, okay. So in that case, what happened? That oscillation takes place in this between that that cathode we supposed to be considered because of that at a micro frequencies the signal time period reduces. So that's why when we reduce the signal time, in that case, that particular the tube will not be worked properly because of that variation in the inductor, that transadmittance. Now consider that supposed to be a transit time. Consider that a transit time is about a 1 nanosecond, and that 1 nanosecond is nothing but what at a frequency of a 1 megahertz. Okay, so and in the then at at a 1 megahertz, so what will be the particular cycle? Okay, so in that case, the transit time becomes for this particular 1 megahertz, it is about a 1 nanosecond there. Then the transit time required for the entire cycle, okay, for the 1 gigahertz. So if you calculate here, now we say that a transit time is about a 1 nanosecond, but that 1 nanosecond transit time for the 1 megahertz of a period of a signal. But if supposed to be transit time is again a same 1 nanosecond at a 1 gigahertz of frequency, so what happened for the frequency when then you supposed to be consider the cycle or a period of the signal at 1 megahertz or a period time period of this 1 gigahertz of a signal. So how much is the time period? So in that case, what happened? The transit time is a large as compared to the period of the microwave signal. Okay. So transit time it will be large as compared to the period of the microwave signal, and the potential between the cathode and gate may alternate from every 10 to 100 times during the electron transit time. Okay, electron transit. So how it is? We say that because here electrons are moving here, it will reach to the plate here. So then alternately, because we supposed to be consider that there is a grid. Okay, and here we are applying a signal, and then in that case the potential at this grid it will be changes alternately, and then when the grid potential supposed to be considered at a positive half cycle, or a grid potential is supposed to be considered at the negative half cycle. So what happened when it is up at the grid potential at the negative half cycle? Then what happened? It removes the energy that given to the electron. Okay, so now generally what happened when your cathode reaches to the plate? Okay, cathode reaches to then it will be absorbed. But what happened when we have the positive half cycle and negative half cycle of that particular grid? So electron get the energy during the positive half cycle, and they produces the energy at the they deliver the energy to negative half cycle. Means energy that electron give up the energy at the okay the negative half cycle, and for the positive half cycle. So what happen here? So they will get the energy. Means energy of that electron will be increases. So now because of this, so what happen here? When this particular we can say that electrons will be moved forward because of that they are getting the energy. The electrons will oscillate in this particular cathode and the grid here. So that's why what happened that cathode and grid space as compared to that particular period it will be a small there. So in that case the electron might return to the cathode. So when if that electron will return to the cathode, so then what will happen? Then the power output of the tube will be reduced. If the power output of the tube is reduces, so then what? Why this power output reduces? Because a plate here, so at this particular plate, so dissipation will be takes place, and at this because electrons will reach to the cathode. Okay, because of the transit time. So the electrons will reach to the cathode, and then they will reduces the a power. If the transit time supposed to be considered that if it is more than that particular cycle there, okay, more than this particular cycle, then what will happen? Then it will reduces the tube efficiency. Okay, so we supposed to be consider that, okay, this one we supposed to be consider that at a what frequencies, what will be the transit time, okay, what will be the transit time. So in that case, how much is the cycle there, how much is the cycles, so how much will be the cycle, zero point 0.1 cycle, zero point 0.01 cycle, 0.001 cycle, how many cycles will be there during that particular period of a time. So that's why we supposed to be consider here what will happen to the transit when we supposed to be considered at a micro frequency due to the transit time effect. So there will be a reduction in the output power of the tube there. So that power output decreases, and then that tube get heated here. Okay, that is about a limitation there. Another limitations, that is about a gain bandwidth product. So in the case of a gain bandwidth product, so generally we supposed to be consider that a bandwidth. Okay, this one is about a gain bandwidth product. So we supposed to be use a bandwidth is nothing but a 2 point. Okay, 2 half power point. So that is about omega 1 and omega, okay, omega 2 and omega 1 here. And we have a conductance, and we have the a capacitance. And generally we supposed to be consider that a gain for a given particular tube, that is about a maximum gain. It is depending upon the a transconductance and a conductance. Okay, it is depending upon the transconductance and the conductance. So now if you consider that a gain bandwidth product, this one, we supposed to be consider A max and BW here. So in that case, what happened? So GM by C. Okay, so we supposed to be write here A max into a bandwidth here. So we'll get that A GM by C. Now the band, if you see here, the gain bandwidth product, that is a constant product. Okay, and that product is depending upon that a transconductance and a capacitance here. Okay, so this one is about a for a given particular tube. So in this case, gain bandwidth product is a constant, and it is independent of a frequency there. Now here we supposed to be consider that a GM and C for a given particular tube, it is a fixed. Now if supposed to be we supposed to be achieve the higher gain. So higher gain means what? That is about we supposed to be higher gain. Then what happen? Even if we achieve the higher gain, so bandwidth will be constant there. Okay, so that particular product will be. Even if we get that higher gain, so then that will limit the bandwidth here. This bandwidth will be the same. Okay, it will be. So we can say that at the higher gain, so that your bandwidth will be a narrow. Okay, so means your tube, it is restricted for the bandwidth. Even if we increase the gain, then bandwidth will be a narrow. Okay, so that is about the gain bandwidth product. So that's why, so we need to consider that instead of a tube, we need to use a reentrant cavities, and that reentrant cavities, that will be used at a higher gain, okay, higher gain as well as the wider bandwidth. Okay, so, or you can say that a broadband. Now these are the limitations of your tube. So that other limitations, if you consider that there are some supposed to be some losses, and that losses are nothing but depending upon that what will be the frequencies to be considered. Okay, so now a RF losses. Now they generally we supposed to be consider there will be a skin effect, then there will be dielectric loss, so there will be a radiation loss. Now generally what happen here, we supposed to be consider that a skin effect loss, that loss due to the skin effect, because there will be a at a high frequency. So what happened, that current at the surface, whatever the for the given particular cross section of the tube, okay, so that will be increased, means resistance increases. Okay, so that's why there will be a resistance loss, and that resistance loss is depending upon the a frequency is there. Okay, so that's why there will be that resistance is nothing but a skin effect for the particular tubes supposed to be, whatever the tubes we supposed to be used here. And that losses due to the skin effect that can be reduced by increasing the current carrying area. So that current carrying area means what? That is about a cathode and a tube or plate, whatever the we supposed to be used in a tube there. Okay. Or if supposed to be area increases, then what happen? Then it increases the interelectrode capacitance, and again it will limit the high frequency operation. That is about a skin effect. So skin effect can be reduces by increasing the area, but it increases the interelectrode capacitance and reduces the frequency operation there. The dielectric loss, it is depending upon that a material there, and generally it is proportional to the frequency, and is supposed to be we use a tube at high frequency, then it will limit that whatever that a dielectric, okay, that this dielectric loss. So this dielectric loss can be avoided by eliminating the tube base and reducing the surface area of the whatever the dielectric material. Again, it can be reduced by placing the insulating material at a point of the minimum electric field. Then a radiation loss. That radiation loss is nothing but at a high frequency we supposed to be considered. Generally, we say that a tube is there, so that tube will be dissipating the power. So that's why the dissipation at a micro frequencies, that is nothing but a loss. So we can reduce that loss by enclosing the tube or using the concentric like construction. Okay, there. So these are about the limitations here. We supposed to be consider that mainly that is about a transit time effect. Okay, because we supposed to know that what will be the transit time angle or a transit time there in a particular tube there. So that's okay. Transit time limitations for a given conventional tube at high frequencies are more because we need to know about a time taken by that electron travel from that a cathode to the a plate there. So that's why that is about a gap. Gap in general we say that this one is about a cathode. We supposed to say that a grid is about a plate here. So this one is from the cathode to plate. This one is about a transit time gap. Okay. So this one from the cathode to the plate that electrons are moving. So that is nothing but a gap. But at a low frequency, the electrons leaving from this cathode and travel to the anode, that will be within a small fraction of a time. Okay, at a low frequency. So generally we say that for a grid here, we supposed to be consider that electrons are moving to the cathode at a positive half cycle of a grid there. Okay, at a positive half cycle of a grid. So that's why at a low frequency, the transit time effect is a negligible. But at a high frequency, transit time is at okay. Now we supposed to be consider that a low frequency now. Okay, that is about a low frequency. The electron will move easily toward the plate, and that a transit time will be negligible. Then at a high frequency, okay, at a high frequency, what happens? The transit time is a large, this one, gap. Okay, we say the transit time is a large as compared to the time period of the signal. Okay, so whatever the time period of a signal, this one is about whatever we can say that a period of your signal. Okay, signal frequency. That is about a period we supposed to be considered. This is about a time period of a signal. So now a transit time is large as compared to the time period of a signal there. So that's why at this frequency, when the electron leaves to the cathode during the positive grid potential, then okay, so we supposed to be consider that a grid potential will be positive or a negative half cycle. If suppose okay, the electron will move when it is a positive. If that grid potential negative, so in that case, what happen for a particular electron passes through this particular grid at a potential, grid potential will be negative. So there, then it will affect the transit time. In the positive half cycle, grid potential attracts the electron. Okay, so then it will because elect, electron will get the energy from that positive half cycle. So that's why so it will attract it toward this a plate here. Because what happen here? They will get the energy from this positive half cycle. But in the case of a negative half cycle, the electrons will repel. Okay, electrons will repel from that particular position there, and then it will reach to the. There will be a repulsion of it. So that's why that electron will move toward the cathode there. So that is about your a transit time effect. Okay, now these are about the limitations of a tube here. So now we supposed to be consider here that a cavity there. So before going to start the two cavity klystron, we supposed to be learn first what are the microtubes we are going to be learn. So there are two types of tubes, microtubes. Okay, so there are two types of tubes. One is about what we can say that a linear beam tube. That is we supposed to say that O type tube. Okay, and the second one is about a we can say that a crossed field tube. That is we supposed to be say that AM type tube. So O type tube or AM type tube. So in a linear beam means what? That beam is supposed to be linear in terms of what? Electric field and a magnetic field. So what happen in a linear beam? A magnetic field whose axis, okay, magnetic field whose axis coincides with that of the electron beam. Okay, means we say that we have the cathode. This is nothing but a cathode we supposed to be consider. So this one is about the electron are moving from this particular cathode there. Now this is nothing but a beam. So this one is about electron moving from this cathode toward the anode here. Okay, so likewise we supposed to say anode or a platinum. So now this one is nothing but a beam. So now this is about the electron beam here and a magnetic field around it. Magnetic field is around it means what? This one. We supposed to be consider that a magnetic field is likewise. Now this one is about the axis of a magnetic field. So magnetic field axis as well as the your electron beam. Okay, so magnetic field whose axis coincides with the electron beam. So that magnetic field will hold the electron beam together that will travel toward this particular plate here. What is the role of a magnetic field? That will hold the electron in a given particular line that will be propagating or that electrons will travel toward this a anode here. So that is about your a linear beam tubes. So now we consider that a linear beam tubes. So there are two types of linear beam tubes we supposed to be used here. That is about one is about klystron, in another is about a traveling wave tube. So in a traveling wave tube, a slow wave structure is used as the interaction region, and in a klystron, a cavities are used. So what happened here in a linear beam tube? So we supposed to consider that a cathode now. So it will emit the electron, and then we have a plate here. That is, we can say that is about a anode plate. Okay. So now electrons are interacting, electrons are leaving from this cathode and reach to the plate. And in between that, there is some interaction region. And that interaction region, that is in here, there may be a slow wave structure or there may be a cathode, that cavity is there. And that in a linear beam tube, what happens? So electron will get the energy from this microwave signal so that that particular energy is converted into kinetic energy, and that they are getting the energy in the particular interaction region, and this is nothing but what, a interaction region there. So because of this particular interaction region, so the electron interact with a microwave frequency signal, so they will be accelerated or they will be decelerated, and because of that acceleration and deceleration of the electrons, they form the bunches, and then that particular bunches travel down toward this particular plate there, and then at some particular place, whatever the bunch electrons are there, there will be some output structure. That output structure will take out that particular energy from the electron. This electrons will give up their kinetic energy to the microwave field. So that's why microwave field will get amplified. And then whatever the electrons are there, those collected, okay, that moving toward this particular place, they, then they are collected at the collector there, or supposed to be a plate here. So that is about a linear beam tube. Then a cross-field tube. So in a cross-field tube, so for here, what happened here? So electric field and a magnetic field are perpendicular to each other. So electric field means what? Here we have a cathode, because we are applying the higher DC voltage, high DC, higher DC voltage, beam voltage to this cathode. So that's why the cathode emits that electron, and so that give up the DC electric field. And we have the DC magnetic field. If the DC electric field and DC magnetic field both are perpendicular to the each other, so that is nothing but a cross field. So now we supposed to be consider that electron beam. We supposed to be consider that a magnetic field. So now both are perpendicular to the each other. So in this case, what happened that electrons are emitted from the cathode, and those electrons are accelerated by the electric field, and that path here, this one is about the electrode here, this one is about the cathode here. So it emits the electron, it emits the electron, and around that there will be magnetic field. So when that electron reaches to this particular region, magnetic field, so they will bend that electron instead of traveling toward this particular plate, so they will be bent here. Okay, so electron will be accelerated because of that electric field, but they will reach to this plate, but because of that magnetic field, they will bend their path, and that path will be bent by the magnetic field. And then that okay, that when that electron path will be bent, so there then oscillation will be created inside this particular tube, and that oscillation is to be used in a magnetron there. So now this one is the concept of a magnetron. So generally we say that a RF field is applied. Here we have supposed to be the anode structure here. These are the anode structure likewise. Okay, so we supposed to be applied the RF field to this anode structure there. And in that case, what happened? The electrons entering the circuit during the accelerating field or the retarding field. So according to that, they will give up the energy, and then they will interact with the particular magnetic field in an interaction region. So that is about a principle used in a magnetron. we'll see that a magnetron in a crossfield tube. So now we talk about a linear beam tube. So linear beam tubes, we need to consider that a, a two cavity klystron. Okay, so in a linear beam tubes, we consider that a two cavity klystron. Then we will consider that a multi cavity klystron. Okay, then we will see that a reflex klystron, and then we'll see that a traveling wave tube. Okay, so now in this here a linear beam tubes, we will consider that a two cavity klystron, multi cavity klystron, a reflex klystron, and this a traveling wave tube. So in this case, in this three component, two cavity, multi cavity, and reflex klystron. So in here a cavity is used as a resonant component at a micro, and a traveling wave tube, a slow wave structure is used as a resonant structure at a microwave frequency. Okay, so now these are about a tubes here. So we'll go ahead with a, what are the various cavities to be used in this particular tube. Generally, a reentrant cavity is used in a two cavity klystron, multi cavity klystron, or a reflex klystron. So that's all about your micro tubes and what are the limitations of the conventional tube with respect to the micro tubes that we have seen today. Okay, and we stop here. Thank you all of you.